Hello everyone, this is Professor Roman. Let's continue the field theory lectures. I want to talk now about the concept of separability. In order to study, in particular, infinite fields of non-zero characteristic, we need some facts concerning separability, some facts that we discussed in the ring theory course. So I will give you these facts without proof. First of all, the definition. Let F be a field. An irreducible polynomial is separable if it has no multiple roots in any extension of the base field. Otherwise, it's said to be inseparable. I guess I should note that I require in the definition that of separable polynomial that it be irreducible. Other authors do as well, but some do not. So you need to be a little bit careful when you're reading the literature. A polynomial little f, it has no multiple roots in any extension of the base field if and only if little f and its formal derivative f prime are relatively prime. An irreducible polynomial little f is separable if and only if f prime is non-zero. Let f be a field of prime characteristic p. An irreducible polynomial over capital F is inseparable if and only if f has the form f of x equals g of x to the p to the d, where g is a polynomial over f and d is positive. So f of x is inseparable if and only if it is a polynomial in x to the p to the d. Moreover, g of x is separable, this g of x, if and only if d is the largest such exponent. And in that case, every root of little f has multiplicity p to the d. The largest exponent d is called the radical exponent of f of x. So for us, perhaps the most important part of this is that an inseparable polynomial will have multiple roots, but all the roots have the same multiplicity, p to the d, where d is the radical exponent. Another corollary, let f be a field. If the characteristic of f is 0, all irreducible polynomials are separable. If f is a finite field, all irreducible polynomials are separable. So if, as is the case, I think, in some elementary treatments of field theory, one assumes the field has characteristic 0, separability becomes a non-issue. Similarly for finite fields. So separability is really only an issue. Inseparability can arise only in the case of infinite fields of non-zero characteristic. If Fe is a field extension and alpha is in E and is algebraic, then its minimal polynomial may or may not be separable. So, definition, if Fe is a field extension, an algebraic element is separable over F if its minimal polynomial is separable. Otherwise, alpha is inseparable over F. Probably should add that clearly. One always needs to mention the base field. Okay. As we have discussed, inseparability of minimal polynomials and therefore elements arises only in the case of infinite fields of non-zero prime characteristic. Here's an example. Let F be a field of characteristic 2, and consider this extension. The t here is an independent variable. We have the field F with t squared adjoined and F with t adjoined. This quadratic polynomial, x squared minus t squared, belongs to, the coefficients belong to f of t squared, but over f of t, it factors into the quantity x minus t squared. So this polynomial is irreducible over the smaller field because it has no roots over the smaller field. It's a quadratic with no roots. In fact, the only root of f of x in the bigger field is the double root t. So this polynomial is inseparable, and t is inseparable over f of t squared. Field extensions can be classified into a variety of types or classes. And by a class C of field extensions, I'm going to mean the family of all extensions that have a certain property or properties. The two major classes of field extensions are the algebraic extensions and the others, which are the transcendental extensions. Okay, those are mutually exclusive and comprehensive. Every extension is either algebraic or transcendental. But within these two major classes, there are several other classes that we have to discuss. Simple algebraic extensions, finitely generated algebraic extensions, finite extensions, finitely generated transcendental extensions. So we're going to take a look at these various types of extensions. So we'll begin with a basic definition. Let FE be a field extension. The following are classes defined by properties of the individual elements. The field extension FE is algebraic, or we would say E is algebraic over F, if every element in E is algebraic over F. So this is a property that is property of the elements of E. The extension is algebraic if all the elements of E are algebraic over F. Otherwise, the extension is transcendental. The extension FE is separable, or E is separable over F, if every element of E is separable over F. Otherwise, the extension is inseparable. So these are element-wise properties. There are some more global properties of field extensions. FE is a finite extension if the degree of E over F is finite. FE is a simple extension if it is generated by, E is generated by a single element. So I should probably say E here. And when this happens, alpha is referred to as a primitive element of E, or a generator, if you want, of F of E. Of F of alpha, of E. I'll get it right. FE is finitely generated. And we also say that E is finitely generated over F if E has this form, if it's F with these smallest field containing F and alpha 1 through alpha n. Finally, Fe is normal if E is the splitting field for a family of polynomials over F. I'm going to give the definition of splitting field later. It was in the ring theory course. Basically, it means it's a field generated by the roots of some family of polynomials. So it's the smallest extension of the base field containing the roots of this family of polynomials. Now, this is one possible definition of normal. But when we give the formal when we get around to discussing normal extensions, I'm going to give you a different definition and then show that the two are equivalent. Okay. But rather than go into this different definition, which is phrased in terms of extensions of embeddings, and that would take us way off base here for now, I gave this definition. It is in many ways the simplest definition of normal extension. Here's some terminology I will use from time to time. An extension Fe is algebraically generated over F by a set A if E is F with A adjoined, where the elements of A are algebraic. So the generators here, the elements of A are algebraic. Similarly, we have separably generated. The elements of S here are separable. Now, we don't want to jump to a conclusion here that algebraically generated extensions must be algebraic, or similarly for separably generated extensions. It turns out this is true, but it requires proof, and we'll get to that in due course. I should also note that a transcendental extension, Fe, may contain algebraic elements. There may be certainly everything in F is algebraic over F, but there may be elements in E that are also algebraic over F. All it takes is a single transcendental element to imply by definition that the extension is transcendental. Okay. The extension QR, the reals as an extension of the rationals, is transcendental because pi is a real number that's transcendental over Q. But there are plenty of real numbers that are algebraic over Q. For example, the square root of any prime. Now, this is our first theorem that relates two types or classes of extensions. Every finite extension is algebraic. So if we have an extension Fe that's finite and we take an element in E and look at this sequence, 1 alpha, alpha squared, and so on, these are the powers of the element alpha, these must be linearly dependent because the extension has finite degree, or E is finite dimensional over F. And so alpha has to satisfy a non-zero polynomial over F. In other words, it's algebraic over F. So every element of E is algebraic over F, and therefore the extension is algebraic. We will have quite a bit to say about towers of fields of length 2. So it's a field extension Fe with an intermediate field. And I'm going to use the following terminology. The extension Fk is the lower step in the tower, and the extension Ke is the upper step. K is the intermediate field, and Fe is the full extension. we're going to be interested in several properties of towers of length 2, and they're defined in the following definition. Let C be a class of field extensions. Let F, E, and K be fields. C, this class of extensions, has the tower property if for any tower FKE, the full extension FE is in C if and only if the lower step FK and the upper step KE are in the class. So here it is in symbols. The class C has the lifting property if whenever the composite is defined, and I didn't need to say that because we've agreed that whenever we use a composite, we tacitly assume that it's defined. But in any case, the extension FE is in, if the extension FE is in class C, and if K is any extension of the base field F, then the lifting K, EK, is in the class. Okay, so we can take an extension in the class, any extension of the base field, lift by that extension K, so KF, KE. Okay, but KF is just K because K is contains F. Right? So we've lifted this FKEK, or in other words, KEK. That's also in the class. Lifting, the class is preserved by lifting. That's the lifting property. C has the finite composite property. If, when we have an extension FE in the class and another extension FK in the class, note the base fields are the same, then FEK, the composite of E and K, is also in the class. And finally, C has the arbitrary composite property. If whenever we have a non-empty family of fields containing a single field F, and whose join is defined, then if each individual FE sub I extension is in the class, then F join of the family is also in the class. So it's closed under arbitrary joins. So I would strongly urge you to go over this definition until you are comfortable with these four properties. It may seem a little confusing at the moment, but it's really not that bad after you've given it some careful thought. But every time we discuss a class of field extensions, we're going to look at these properties to see if they hold or not. Sometimes it's going to be easy to tell, sometimes it's going to be very difficult. Notice also that one half of the tower property and the lifting property together imply closure under two and therefore finite composites. Then to see what I mean exactly, suppose FE and FK are in the class C. Then this extension, FEK, so this is the join, or composite, can be decomposed into this tower, FEEK. The first step is in C by assumption. The second step is a lifting of the first step, FE, by K. So if the relevant half of the tower property, namely if the two pieces if the lower and upper steps are in the class, then the full extension's in the class. If that holds, and if the lifting property holds, then FEK is in the class. And so the composite is in the class. Okay? So these are not entirely independent properties. If you have half of the tower property, namely if the two individual steps are in the class, implies the full extensions in the class. And if you have the lifting property, you have the finite composite property. So here it is. If a class of field extensions, I don't know what there's doing there, has the tower and lifting properties, then it also has the composite property. But it doesn't have to have the full tower property, just half of it. Okay. All right, now, an important definition. A class C of extensions is distinguished if it has the tower property and is closed under lifting, or the lifting property. And therefore it will have also the finite composite property. So class is distinguished if it has these three properties. A class C of extensions is strongly distinguished if it's distinguished and also is closed under arbitrary composites. The term distinguished is actually in common usage, but I have not seen the term strongly distinguished used elsewhere. So I guess you would have to say it's my term, but we will have some use for it. It seems pretty harmless, so I included it. As we're going to discover, almost all of the field extensions that we're going to study have the lifting property, all but one, the transcendental extensions. Also, many of them possess either the tower property, and therefore the finite composite property, or at least a portion of the tower property. I wish I had good names for the different parts of the tower property, the two halves in particular, but I couldn't think of anything clever, and so I didn't do anything. So for example, the class of normal extensions has the property that if we have this tower of length 2, and if the full extension is normal, so is the upper step. But the lower step doesn't have to be normal. Also, the normality of the individual steps does not imply the normality of the full extension. So, of all the pieces that go into the tower property, normal extensions just have one small piece, important small piece. Here's a table that I compiled. I don't know if it's going to be of use to you or not, but it lists classes of extensions, some of which we have not yet even mentioned, but will in due course. Abelian cyclic extensions, polyabelian or solvable extensions, radical extensions, Galois extensions. Haven't discussed any of those yet. An extension is Galois by definition if it's both normal and separable, so that's nothing new. But these others are new. And the extensions that are in bold, algebraic, finitely generated, and separable, have the tower property. And since they have the lifting property, they're distinguished. The ones that are not in boldface, while they all except one have the lifting property, they only have a portion of the tower property. The most common being that if the full extension has the property, then both steps, well, actually that's not the most common. I guess there really isn't anything that would be considered really common. Full extension implies both steps. Full implies upper step, also here. Both steps imply the full. Full implies at least one step. So the tower property is a little more complicated in terms of which extensions satisfy it and which don't. The lifting property is pretty straightforward. Just by way of terminology, if C is a class of field extensions, then we'll say that a tower of fields is in a class C if every one of the steps, fk to fk plus 1, is in that class. So, for example, I would say this was an algebraic tower if each of the n steps is algebraic. And similarly for normal tower, separable tower, and so on. Let's now take a look at simple algebraic extensions. If f with alpha joined is a simple extension and alpha is algebraic over f, then we saw earlier that the field f with alpha joined is the field of all rational expressions, rational functions in alpha. Suppose that the minimal polynomial of alpha over f is, we'll call it m of x, has degree d. Then we can improve considerably on this characterization of f with alpha joined, because for any element f of alpha over g of alpha, g of alpha is non-zero, so g of x is not the zero polynomial. And g of x and m of x are relatively prime. And therefore, there exist polynomials, this is Bezo's identity, a of x and b of x, for which this equality holds. Evaluating at alpha tells us that a of alpha, g of alpha is 1, because m of alpha is 0. So g of alpha is invertible, and its inverse is a of alpha, which means one of these rational expressions in alpha is in fact a polynomial in alpha. So our description of f with alpha joined, again, remember this is for alpha algebraic, doesn't work if alpha is transcendental. Then f with alpha joined now is the set of polynomials in alpha over f. Moreover, if the degree of this polynomial little f of x is greater than or equal to d, that's the degree of the minimal polynomial of alpha over f, then we can divide. The remainder has degree less than d, and again substituting for alpha for x, f of alpha is the same as r of alpha. So this is a further improvement. F with alpha joined is the set of all polynomials in alpha of degree less than the degree of the minimal polynomial of alpha. These polynomials are distinct, and I'll leave that for you to demonstrate. And so it follows that as a vector space, f of alpha as a vector space over f has basis 1 alpha up to alpha to the d minus 1. And the degree of f with alpha joined over f is d, the degree of the minimal polynomial. That's the degree of this extension, also called the degree of alpha over f. Okay. So that gives us the additive structure, As to the ring structure, the multiplicative structure on F with alpha joined, if you look at the evaluation at alpha map, it simply takes any polynomial and evaluates it at alpha. This is a ring homomorphism, and in fact is surjective, and its kernel is nothing more than the ideal generated by the minimal polynomial of alpha. So the first isomorphism theorem of ring theory tells us that the induced map from the quotient ring here to F with alpha joined is a ring homomorphism. And as a consequence, if alpha and beta are conjugate over F, if they have the same minimal polynomial, m of x, then they are isomorphic. In fact, if you take the inverse here, when replace alpha by beta, take the inverse and so on, it's the composition of one of these evaluations with the inverse of the other one that will give you what I would call, say, the replacement map that replaces alpha by beta. Okay. So I guess it's, you take the inverse of the epsilons of alpha bar and then apply epsilon sub beta bar. Okay. Anyway, so this replacement map fixes all constant polynomials, so it fixes the base field. Okay. And it's an isomorphism. So here it is in summary then for what you would call simple algebraically generated extensions, generated by a single element that's algebraic. So let Fe be a field extension, alpha B and E be algebraic. Then F with alpha joined is this set of polynomials of degree at most d minus 1. D is the degree of the minimal polynomial of alpha. The extension is finite, and it has degree equal to the degree of the minimal polynomial. That's also referred to as the degree of alpha over F. This set is a vector space basis for F with alpha joined over F. The evaluation map induces an isomorphism between F with alpha joined and this quotient polynomial ring, which is a field. M of x is irreducible. This is a maximal ideal. The quotient is a field. And if the elements alpha and beta are conjugate, then the replacement map is an isomorphism that fixes the base field. A consequence of all of this is that the following are equivalent for a simple extension. Alpha is algebraic. The extension is finite. All finite extensions are algebraic, as we've seen. The extension is algebraic. Okay, so we have three conditions that are equivalent. Alpha is algebraic, the extension is algebraic, the extension is finite. And when any of these, and therefore all of them, hold, the degree of the extension is the degree of the minimal polynomial of alpha over F. Here's an example. Consider the fields Q with the square root of 2 and cube root of 2 adjoined. These are the positive roots. And Q with the sixth root of 2 adjoined. Since this, if we take this generator here, this primitive element for this field, we square it, we'll get 2 to the 1/3. If we cube it, we'll get 2 to the 1/2. So that tells us that this field is contained in this one. So we have this little 2 tower. The 6th degree rational polynomial, x to the 6 minus 2, has this as a root. Okay. So we know this, this is a rational polynomial over q. So we know that the full extension has degree at most 6, the degree of this polynomial. This may not be the minimal polynomial, may or may not be, but it is satisfied by this element, 2 to the 1/6. Okay? But notice that this extension does have degree 2, because square root of 2 has minimal polynomial x squared minus 2. The multiplicativity of degree tells us that this divides this degree, which in turn divides this degree, which is, as I said a minute ago, is less than or equal to 6. Do the same thing with this simple extension. 3x cubed minus 2 is the minimal polynomial here. You'll have to check that. And we have the same divisibility here. So what we have is that this degree in between here is divisible by both 2 and 3, therefore by 6, but is less than or equal to 6, so it's equal to 6. And that tells us that this guy, this field, has degree 6 over q. That does make this the minimal polynomial. Oops, sorry. X to the 6 minus 2 is the minimal polynomial for the 6th root of 2, and these two fields are in fact the same. Okay. So this is a really good example to study. It does a lot for us, showing us that the tools we've developed can be quite powerful. Okay, this sentence shouldn't be here. Okay.